Yeah, so thank you for the nice overview and nice introduction. Oops. Let me just say a little bit about people involved in case I run out of time at the end. So as Matthias said, I'm focusing here on upcoming big data analytics developments within NOMAD rather than the infrastructure and the database, which will be covered by Marcus tomorrow. So I'm going to be talking about work done in my group at Warwick by the NOMAD team here. So Sasha, who joined us a few months ago now. Also in Gabor Chinese group in Cambridge, James Darby is the NOMAD postdoc working there. And I'm also going to talk briefly about some work done in Luca Giringhelli's group at the Fritz Haber Institute by Andreas in particular. So that's going to be another application towards the end of the talk. I want to say a little bit about NOMAD and its history, just to contextualize what I'm going to say about analytics later on. So as you will all know, NOMAD is originally conceived as a laboratory, and now we have also a center of excellence. So the NOMAD laboratory enables fair sharing and use of computational material science data. And as I say, you'll hear a lot more about the underpinning infrastructure and particularly how it's been reinvigorated recently by Marcus Schneiden tomorrow. But the basic idea is that it's a system in which one can publish data by uploading it, making it widely available, and converting it into a common format, which is normalized and hence interoperable, and then also to explore other people's uploads and to either download them in the original form or in a unified form. And then importantly, for what I'll be talking about, to make analytic comparisons between data uploaded by other people and build models trained on that data. And that's what we'll be looking at some examples of. The NOMAD Center of Excellence is a new initiative that kicked off a year or so ago to build on the successes of the original NOMAD project. And the aim really there is to bring computational materials science to the exascale. So there are 3 parts of that project. Again, I'll be focusing on the third of those, but just to introduce briefly the other 2, they are the first pillar on taking electronic structure codes and making them ready for exascale computing that's upcoming. Once you have an exascale computer, an important way to make use of it is to deploy workflows that can be used for high throughput computing in a resilient fashion across a very large computational domain. And that's one effective way to make use of very large scale computing resources. So that's the central pillar of NOMAD. And then the third pillar, what I'll be focusing on today, is the big data analytics. So what you do once you have a large body of data contained within an archive or a repository. As well as those 3 main pillars, there's a number of cross-cutting activities that make sure that software and hardware design are connected and interrelated. That's co-design, and that guarantee the integrity of the underlying data infrastructure, as well as supporting a number of highlight applications. So in a little bit more detail, the first pillar is focusing on developing and updating existing DFT and beyond codes and giving them the performance enhancements that are required for them to operate at the exascale. In the workflow pillar, the focus is on high throughput computing, and often with a combination with beyond DFT workflows. So not just standard DFT, but really advanced Green's function methods, etc. And then in the third pillar that I'm involved in and lead together with Matthias and Luca, what we're trying to do is take the existing NOMAD analytics toolkit, I'll show you a couple examples of that shortly, and expand upon it and develop it to bring it towards near real-time performance. And I'll try and articulate more clearly exactly what I mean by that as we go through this presentation. As is not a surprise to anybody engaged in this community, NOMAD is one of the pillars within FAIR-DI and fully supports fairness. And I'm sure that this will be something that Marcus talks about in more detail, but just to very briefly motivate how NOMAD achieves each of the FAIR principles, I'll go through this briefly now. So for repository contents to be findable, it's important to allow users to assign DOIs to them and to include them together with publications so that a data set can be easily located. You can also query the NOMAD platform either using a simple GUI or using the Optimade query language in order to find records that match particular requirements. once you have a unique identifier, it maps back both to the metadata and also to the original files that the user uploaded. So that enables accessibility and also helps with reproducibility, that the calculation can be recomputed using the original input files. Interoperability is guaranteed by normalizing data to a common ontology that, again, you'll hear more about from Marcus tomorrow, but is also a key enabler for doing any analytics. So analytics relies on the code-dependent data being converted into a common form so that different code concepts of similar quantities can be harmonized and brought together. And finally, I mentioned already reproducibility, but I think the work that we're doing at the moment on expanding the capabilities of the data analytics and the workflow will also provide improved mechanisms to ensure reproducibility, giving users easy ways to run analysis themselves in a cloud environment and to quickly verify previously published results. In order to deliver that, what we think is necessary is to take existing AI and machine learning tools and try to invest them in sufficient optimization that you can have a real interactive experience when using these tools. That's what we will be doing in the remaining 2 to 3 years of the activity. So we've made some preliminary progress that I'll tell you a little bit about so far, and then there's quite a lot of exciting plans coming up over the next couple of years. So there are 4 different analytics methods that we're targeting in NOMAD. I'll talk today about the first 2, neural networks and kernel methods, and there's also a lot of activity in the FHI group on compressed sensing techniques and subgroup discovery. And once these analytics tools have been developed and deployed on the NOMAD infrastructure, we'll be applying them to carry out applications that wouldn't have been possible before. So where did we get to at the end of the last NOMAD project? Well, a lot of useful tools were developed that enable you to do things like query the archive and construct data sets which can be used to train models. There are some really nice demonstration notebooks available that you can have a look at. I've just reproduced a couple of snapshots here to show you how you can do things like identifying all the structures that match a particular set of requirements, or a notebook that was just put together recently by Andreas that describes this Arise tool that I will be saying a little bit about towards the end of the talk. And these leverage the contents of the archive. They allow you to build analytics models that take information from a wide variety of different sources. But at the moment, that's somewhat cumbersome to do, because if you want to perform a complex calculation, it typically has to be done for each record that is returned as a result of your query, and that can take quite a long time. So just one example here of something that takes a few minutes to apply and doesn't really give a true interactive experience. And so it's hard to interactively explore and construct models as you go along. We've been analyzing what is needed in order to make that experience a bit more intuitive and to allow freedom and creativity when constructing data science type models from the vast quantity of data which is deployed within the NOMAD archive. And there are a few things that are needed. I'll be talking about 3 out of the 4 of these in this talk. So the first thing is to be able to very quickly and through the use of large computing resources evaluate what we call descriptors, so special features of the atomic structures that have been uploaded, which are invariant to physical symmetries, to combine those representations into kernels between pairs of structures or pairs of environments, and then to use those in the second point to build models that can predict particular properties. So that could be using kernel methods, or it could be using neural networks. And when we're thinking about kernel methods, we're particularly interested in the case where the training set grows dynamically during the course of an investigation. So where we automatically pull in more and more reference data that results from querying the archive and obtaining structures of interest. Then there's a final topic on compressed sensing that I won't be touching on today. So what do we have in mind? What would be a sort of typical use case that motivates the kind of interactive explorations that we'd like to be able to do? Something like mapping the contents of the archive is a good sort of picture to have in mind for the kind of task that it would be nice to be able to carry out. So what I've shown here is a representative low-dimensional map of a large database of configurations of silicon, and it's projected into a 2D low-dimensional space. So this is a kernel PCA map, actually using the SOAP descriptor as the original fingerprint for the structures, but it gives a very useful and intuitive overview of the contents of a large database. We can look at the part of the space that corresponds to diamond structured silicon, amorphous silicon, various different polymorphs, a large region associated with liquid, and then various crystal structures that are distinct from one another in this two-dimensional projection. So being able to quickly and easily explore all of the structures within NOMAD, so the last count was around 11 million structures uploaded, and produce these kinds of maps for particular queries and subsets is our sort of interim goal, one of the deliverables that we're working towards currently. And in order to do that efficiently, these descriptors have to be pre-computed and stored as part of the repository. So we have to augment the structures within the database with the required physically invariant representations. So you might have come across symmetry functions that are used for fitting Baylor-Paranello style neural networks. I'll say a lot more about the SOAP, the smooth overlap of atomic potential. And then there's a new class of fingerprints, the atomic cluster expansion, that we're planning on adding in future. And then once you have those descriptors available for each atomic environment or for each structure within a database, there's lots of things that you can do with them. In the first case, mapping or charting and identifying structures with common behavior, but then later selecting a subset of those structures and using them to build a model will be the next topic that I'll talk about shortly. But in all cases, these descriptors need to be efficiently pre-computed and stored. And what's particularly challenging about this is that most of the machinery that has been developed for these kinds of tasks up until now has been used to fit interatomic potentials. And in that regime, you typically have a fairly low number of chemical species, and you don't worry too much about the scaling with the number of different types of chemical elements involved. So if we go on and look at how this is actually represented, if we think about SOAP, the smooth overlap of atomic positions, what we're doing here is constructing a density by putting Gaussians on each atom within our structure, adding up contribution from each of those neighbors around a particular atom of interest. So we're looking at the environment associated with the central atom in this methane molecule here. That gives you permutational invariance because we're summing over all of the neighbors, and also translational invariance by construction because we're only interested in vectors joining a neighbor to an atom, but it doesn't remove the rotational symmetries. And so the way that this is done is by taking a density representing one environment of interest, multiplying it by a density with which we'd like to make a comparison. So this is a kernel between densities, and we need to do that for all possible rotations. So we take one structure, we keep it a fixed orientation, we take the second structure, rotate it over all possible rotations, and then look at the overlap between those densities. It turns out that that integral can be done analytically if one makes use of a projection of the density into a basis of spherical harmonics and some arbitrary choice of radial basis function. So it doesn't really matter what you use for the radial basis function. If you use spherical harmonics, this integral becomes analytically tractable for a discretized representation of the density. So there's still some approximation involved in where we truncate this sum, where we cut off in terms of our radial basis set and our maximum angular momentum L. But once those things have been fixed, this integral is analytic, and actually it collapses just to a power spectrum of these expansion coefficients for each environment, and then evaluating the kernel itself is as simple as dotting together two power spectra vectors. Okay, that's all sort of fine for a single chemical species. Where things get difficult, particularly in the NOMAD case, where we may be interested in the entire periodic table of chemical elements, is when we introduce multiple species into this representation. So now I'm summing over species alpha, and I end up with two additional indices depending on the chemical species of each of the environments. So the length of the vector which characterizes these environments has a quadratic scaling both with a number of radial basis set elements that I use, and also with a number of chemical species S. So N is the size of the radial basis set, Gn. S is the total number of species here. What we're interested in doing before we go ahead and evaluate across the entire NOMAD database is finding a way of doing this compression in a way that doesn't depend on the particular choice of data set, so that we can apply a common recipe across a vast range of data, and that preserves as much information as possible and can still be used as a good descriptor for mapping and also for regression. So this is what James Darby has been working on for the last year or so as part of the NOMAD project, and he's really made some critical progress and some very nice insights that I'll try and talk you through now. So his first observation was that we can split the contributions to this power spectrum into different slices that correspond to a given angular momentum. So we can look, for example, at the first row in this matrix here. We can rearrange the contributions to the power spectrum into a series of dot products between expansion coefficients, each at a given value of L. And this is the L equals naught row. And providing those vectors form a basis, then we can recover full information in this matrix from only the first two L plus 1 rows. So for L equals naught, we only need 1 row. For L equals 1, we need 3 rows, etc. And we can then exploit this to save having to represent the entire matrix and represent only the coefficients we need to reconstruct it. So far, this is a completely lossless compression. We'll go on to talk about lossy compression shortly. A way that James introduced for thinking about this that generalizes nicely is to take the original fully multi-species description of an environment with some sort of body order here. Typically 2 is used for existing implementations of SOAP, and to augment it by a density which is agnostic to the chemical species. So we'll look at some sort of limits of this. This is the standard element sensitive part. This is an element agnostic contribution, and we can see various ways we can choose these 2 parameters and put things together. So this is the conventional description that's been widely used up until now. That's quadratic scaling, both in the number of species and the size of the radial basis set. And there are various things we can do to reduce that scaling at the cost of introducing some ambiguity. So atoms that are shown in gray here are no longer distinguished by the descriptor. So the original representation distinguishes everything. And if we totally ignore species information, we come to mu equals 2. So we have only this element agnostic contribution. We don't have this part at all. We only retain positional information and not chemical species. Conversely, we can reduce the scaling with respect to the radial basis set by reducing these exponents to 1. The hat here corresponds to projecting onto the unit sphere. So as well as retaining full information about where neighbors are located, we can imagine projecting them back onto the unit sphere represented by the dashed line here, and that reduces the complexity further. So in the extreme case, we only consider the angular information about where neighbors are located, and we can still distinguish them different chemical species. We can go even further and project onto the unit sphere and also remove chemical incantation. This is quite a nice systematic way to construct a series of approximations to the original descriptor. And you can look at what those correspond to and the scaling associated with each of them. So our original, where is it? Our original guy up here, nu equals 2, is the quadratic scaling with respect to both radial basis set size and number of species. And we can introduce approximations which are either linear or totally invariant to number of chemical species, and then go ahead and try them out and see how well they work on large sets of data extracted from the NOMAD archive. So let's have a look at a couple of examples. First, we picked actually the widely used QM9 data set. So that contains 5 different chemical species. However, they're all in equilibrium configurations. So what's interesting to note here is that species information isn't actually completely crucial in order to be able to distinguish these different molecular environments. So let me talk you through what's going on here. This histogram here shows you how many numbers you need to represent the structures. So the original complete representation is just over 4,000 elements long, whereas the fully compressed version, which has removed all species information, is much, much shorter, only 180 elements required. And what we're showing here is the number of, as the number of training structures increases, what the accuracy in a regression model is, the maximum absolute error in a regression model. We considered two different types of regression model here, either simple linear models or kernel-based models. And what's interesting is that completely removing all chemical species information does reduce the accuracy compared to the original, but maybe not as much as one might have thought. Whereas with a linear model, there's nowhere near enough information left to reconstruct the original environments. But taking a look at some of the more intermediate results, we can see we really can get very good compression with very little loss in accuracy. So taking, for example, the green model, we've reduced the size of the descriptor that we need to store by a factor of 4 with very little reduction in accuracy. So this is with a moderate number of chemical species. The next example is with an extreme number of chemical species. So this is an alpacylite database with 39 different chemical species contained within it. And the results that we get are similar, although the compression ratio is even more stark. So going up from the fully quadratic in both species and radial basis set size of over 200,000 elements in the vectors that we'd have to store, down to 180 for the maximally compressed version, which admittedly is not going to do very well here because it's not possible to reconstruct environments just based on geometry. In this case, it's like a random alloy. You can swap two chemical species, and that change can't be inferred from looking only at the positions in the same way that it could perhaps from looking at the structure of an organic molecule. So here it would be more appropriate to pick some of the compressions which are less extreme, which retain both positional and chemical information, but you can see we can still get quite significant compression. These DJ here are where we've optimized an embedding from the original 39 component species to a much smaller number of effective chemical species. We've projected that domain down into 2, 3, or 4 dimensions. The dashed line are results reproduced from an earlier work that optimized these embeddings very carefully. What we've done here instead is just select the embeddings, and you can see we can get, in the limit of very large training structures, comparable performance to the carefully optimized embeddings. Also, the simpler approaches that involve just reducing the exponent in both the element sensitive and element agnostic forms can give significant compression and not too much loss in accuracy. Okay, so moving on to the next topic. Once you've found an efficient representation of structures, one would like to use that to build models, to make models that can be used to predict properties. Just give an example of something I've been involved in a few years ago now. So a typical application, and the way that we used to do it in the sort of offline regime, is to carefully build databases of density functional theory calculations, about 2,500 in this case, which contain a large number of chemical environments. And then in order to make the calculation tractable, we have to sparsify that to a much smaller selection of representative environments with which all others are compared in order to build a kernel model, which also in this case included a repulsive component just to take account of what happens when atoms get very close. So the linear algebra involves selecting these representative environments, comparing them to one another, and comparing them to all elements of the full database. And this product here is essentially a low-rank approximation to the full kernel matrix between all 170,000 atomic environments, which we can't afford to either represent or compute. So this is the approach we've used until now. It requires a very large computer, even with this sparsification, to store these these matrices. I won't say too much about the Bayesian error, but it's a successful approach that builds accurate models and can also incorporate information from total energies, forces, and virial data. So we can learn equivalently from various different classes of data, providing they're linearly related to our original observations. And we can also make predictions that come along with uncertainties, so with posterior variance estimates, because we can interpret this kernel ridge regression model as a Gaussian process and look at the posterior variance of the predictions. But if we'd like to bring that to exascale and to near real-time performance, as well as being able to evaluate the descriptors efficiently using approaches like what I've just been talking about, we need to be able to fit models very quickly and in a massively parallel way as well. The code that is used to do this at the moment is multi-threaded. It makes use of OpenMP to speed up calculations, but it wasn't data parallel before. So what Sasha has been working on for the last few months during his time in the NOMAD project is data parallelizing this code. The main goal for that is to lift the restriction on the total amount of memory, but we're actually finding that it also gives a speed up in the time taken to solution as well, which is very encouraging. So previously, one had to have access to multi-terabyte nodes in order to carry out moderate size fits, and it gets much worse if you start looking at high entropy alloys, etc., due to this quadratic scaling. Although it looks like there are significant avenues to reduce that cost. And what Sasha has done is distributed this large K and M matrix. I'll show you a bit more how that's done over nodes, and then to use Scale APAC to do the QR factorization. So this is the same equation as before. That's what we're trying to solve, actually. We don't invert this matrix directly. We build a related linear system, which consists of an augmented matrix. This is the uncertainty information, the weights on our training data. And then we do a QR decomposition of this very large matrix. So the way in which we've parallelized it is to take your very long, thin matrix of training data and domain decompose that across a potentially large partition and keep track of the corresponding right-hand side vector and put that in the right place. And then we can do a decomposed QR factorization and get the fit coefficients back. So it looks like it's working very nicely. Around 95% parallel efficiency at the sizes that we've been able to test on so far. And we're also carefully checking that the potentials that we train in this way are equivalent to the ones produced with the earlier code. So we're hoping that when this is coupled to the NOMAD infrastructure, a user would be able to go ahead, make a map, select a range of training data, and then produce an interatomic potential in a semi-automated manner very quickly. Okay, finally, I want to say a little bit about some work that I've not been involved in that is from Luca Giranghelli's group in the Fritz Haber Institute, so within NOMAD, but not involving me directly, and was carried out primarily by Andreas. So this is an approach known as ARISE, artificial intelligence-based structural evaluation. And it's a neural network classifier, but the sort of unique feature of it, which I think is really appealing, is that it's not using a standard neural network, but instead using a Bayesian neural network, which has the advantage that the weights in the neural network are not just point estimates, they're probability distributions. So it gives you a way to quantify the uncertainty in the classifications that are made by the model, which I think is very nice and very appealing. And so this has been applied to a selection of different materials, ranging from elemental solids up to nanotubes and beyond to increasingly complex material systems. The basic idea is that you have some initial structure, you represent that with an invariant descriptor. Andreas is actually using SOAP in a similar way to what I've described, but it has to be averaged over the structure to produce a single representation of the entire structure, not just a local environment. That's then fed into a Bayesian neural network, which predicts the class of the material and an associated uncertainty. And it can also be used in very large polycrystals by looking at individual subdomains within the system and comparing them to one another. And you can see Bayesian uncertainty predictions coming out here. So it's identifying the grain boundaries between the different domains and giving an associated uncertainty to that prediction. It can be applied to very large and very complex systems and can incorporate experimental data. So this is electron microscopy data and the Bayesian uncertainty estimates that arise from the mutual information can be very useful in identifying where grain boundaries are situated within the material. I think if you're interested in finding out more about that, I'll put some information up, and it would be good to talk directly to Andreas, Luca, or Angelo about that. I wanted to pick up on one more point. So they validated their predictions against other state-of-the-art methods, with the main advantage being the associated uncertainty that goes with the predictions. So a little bit more information. The paper has just been accepted and will be coming out shortly, but the archive preprint is already online, together with the code and the tutorial that I showed a snapshot from earlier on. Okay, I want to pause a little bit and think about future plans and what we need to do in order to get towards the capabilities that we would like to add to the data analytics platforms within NOMAD. So I talked a bit about the compression of the environment description. The next step is deploying that throughout the existing data. We're working on that at the moment. And then a very nice enabler for that is something that I think, again, Marcus will probably talk about tomorrow. It's the NOMAD Oasis, which is a way to set up a local deployment of NOMAD within your own institution. It means you can hack around making changes to the code without worrying about impacting on the central database. So we've been using that to test out these new approaches and start to deploy them at moderate scale. The next step after that will be to build a tutorial or an example of building and visualizing these maps of materials as a result of a query. And I think that will be a really nice proof of concept. Something that we haven't devoted much thought to yet, but I think is really important, is query versus compute. So it's clear that we need to pre-compute and store expensive things like SOAP descriptors. But once you've got a descriptor, the comparison between two environments is relatively cheap. So you take a vector describing one environment, a vector describing another, dot them together and raise it to some power. So it's not clear that storing kernel matrix elements is worthwhile, particularly as the scaling is quadratic, of course, in terms of memory. But probably comparing each structure within the overall repository to a number of landmark structures to enable you to roughly locate it would be worthwhile. That's something that should be explored more. I talked a bit about adding support for other features, particularly this atomic cluster expansion, which is gaining a lot of ground recently because it provides a complete description and has been formally shown to do so. Deploy and make available the automated construction of potentials as a result of carrying out queries on the archive. And a final step that we'd like to do is to augment the fitting of models with an outer loop that allows subsampling from the training data set, which will be another way of producing uncertainty estimates for interatomic potentials. So I'll just finish with some overall acknowledgements for the presentation as a whole. Sasha and Albert have been working with me at Warwick on the parallelization of the gap fitting code. James and Gabor and I are doing the compression of the environment description. Andreas, Angelo, Luca, and Matthias at the Fritz Haber Institute. And then, as you'll hear more tomorrow, there's been really a lot of sustained effort on reloading and reinvigorating the NOMAD database itself. Okay, thanks very much.
Great. Thank you very much, James, for telling us about several new developments. At least I had not seen some of them. Very interesting. So questions, and I see actually Gianmarco has his hands up already. So Gianmarco, please.
Yes, I'm okay. So I was wondering, James, when you use the SOAP, are you aware of cases where SOAP descriptors have been used to predict the properties of materials? I know that you are using more for predicting interatomic potentials, but are you aware of cases where those descriptors were used, you know, for instance, with CISO or with other methods to predict properties?
Yes, I think there has been quite a bit of work on using them as input directly into structure property maps. so for example, the last example that I talked about briefly does use a form of soap as an input into this classification of crystal structures. And that's quite a good example of jumping over the need to produce an interatomic potential and directly targeting properties. I think that will be a good example. I'm sure there are others that I can't immediately bring to mind, but that will be a good starting point.
Yeah, actually, I had a similar question, but before that, again, the Louvain people are probably half the volume than I have from James. So maybe you can speak up louder. That would help. So along the same line, so the SOAP descriptor is certainly a structural descriptor, right? So structural properties you could describe. If you go to electronic, I guess you would need another one, or adding something, or how would you do that?
Yes, yeah. So we've coarse-grained out the electronic structure completely here. We're only representing atomic and chemical species information. And I think there's a lot of exciting future prospects for directly represented electronic features. And I think ACE is a particularly powerful way to go in that direction. And there have been some very recent developments looking at fully equivariant representations of Hamiltonian matrices, etc. So I think that would be an exciting way to go. Yeah, a different set of target properties and potential problems associated with degeneracies between the atomic environment and the electronic structure. So level crossings, etc., would be very hard to capture without incorporating some additional degrees of freedom somehow.
Yeah. So Luca has a comment in the chat, which let me actually put this in my words. So we had, I would say, in the Tycho-Brahe-Kepler concept, right? Actually, against that concept, we basically put a lot of data in the Kegel competition, which is really allowing everyone in the world to do really looking at data, and that was actually cohesive energies and electronic structure and band gaps. And with these data, there were roughly 900 different groups contributing with different methods. And Luca is just, so again, that tells you what, if you have data, you will be surprised what people do with these data. And they come up with methods which you didn't know. The second place, the second best was something which we roughly knew. And that was, in fact, a SOAP implementation. So just telling also that it's actually a very successful method, I think.
Yeah.
Are there more questions? I would have one more, because you mentioned the way I understood it, that you have some, in my words, transferability from one atom type to another atom type.
Yes.
Yeah, can you explain that a little bit, actually, why and how this works?
That's a good question. I think developing an intuition for it is rather more challenging than exploiting it. But if you think about a random alloy as a sort of extreme case, it's clear that not all observable quantities depend on the exact chemical species located at each site within the alloy, and some kind of alchemical representation which blurs the distinction between one chemical species and another should be able to capture a large fraction of the output quantities that you're interested in. And I think that's the sort of direction that we're going in, removing the full description of species and blurring it somewhat.
I mean, that would be a little bit in the spirit of what we call, say, the virtual crystal approximation, that you somewhat really average it, and that information, of course, should be there if the systems are not too different, right? But if so that means if you really go from a very different chemical system to another one, then you probably need some different description or some different learning.
Yes. Yes, I think that's where optimizing these embeddings and identifying where these things are transferable and where they're not is important. And what we were trying to do here was identify something that's appropriate for the vast array of structures in NOMAD, and so isn't hyper optimized and just gives us sufficient compression that it's tractable without throwing away too much information. And it does look like dropping from quadratic scaling to linear scaling is probably the sweet spot there. We still retain some chemical species information, but not the full original complexity.
Okay. More questions? Hands up or in the chat? Nothing in the chat yet. So coming again to this thing which you mentioned as one of the motivation, bringing really the machine learning to a real-time experience. So you said a little bit. So you're doing really, you're going in towards, say, having the system in a massive parallel, right?
Yes, there's sort of two components. So I guess the first step is having the input data available, and that can be done by pre-computing essentially. You can take each structure in the archive and augment it with the descriptor, and that can be done as things are uploaded or in a pass at some point beforehand. But what we can't anticipate is which structures are going to be compared with which other structures by the user when they want to build a model. And so that has to be done through exascale parallelization, and the construction and diagonalization of the kernel matrix can only be done once you know what you want in the model of interest. So that's where we're having to put the effort into the parallelization, I think.
Okay, thank you. Gianmarco, can you unmute yourself?
Probably muted. Can you hear me?
I can hear you, yes.
Yeah, okay. So I wanted to ask maybe a naive question because I'm not very familiar with SOAP, but if you were to get the SOAP descriptors for a structure, sorry, would you be able to know what the structure is? Is it bijective in a sense? Or
it's a very good question, and the answer is no. And that's why these newly introduced ACE features are particularly appealing, because they are complete and hence invertible. So there are examples of pathological configurations that have been recently published, actually, just recently identified, for which two configurations map to the same SOAP vector, and so it's not bijective and therefore can't be inverted. They're a bit unusual and haven't posed a problem in terms of fitting of interatomic potentials, but you can find these particularly special configurations, and I think it's very, very interesting to try and understand and exploit them. But ACE manages to overcome that particular limitation, and as I said, has been formally shown to be complete mathematically, so is invertible.
Thank you very much.
Okay. Good. So we continue the discussion in a more general way at the very end of this session.